Hello statistics students, my name is Emigh, and this video starts our discussion on section 4.3, title, complements, and conditional probability. All right, we're going to start talking about complementary events. Let's talk about our notation first. We're going to use a capital A for one event, as we have in the past. And then notice this right here, same capital A, but it has the bar over top. A and A with the bar over top are what we call complementary events. Let's elaborate. A bar is the complement of A and is often read not A. So this one we read A, this one is often read not A. The probability of event A and its complement have to add to 1. Notation, capital P open parentheses of A plus capital P, so probability of not A, equals 1. Little Venn diagram to help explain that. It means that the probability of event A occurring, or, so plus, the probability of event A not occurring has to cover 100% of the space. And we know that 100% is the same as probability of 1. So the probability of event A occurring plus the probability of event A not occurring must equal 1. It is impossible for an event and its complement to occur at the same time. For example, if the probability of an event is 0.87, what do you think the probability of its complement is? If your mind went to 1 minus 0.87, so 0.13, that's nice. That would be using this formula right here. Probability of event A not occurring would equal 1 minus that 0.87. Another example, a sample of United States adults were surveyed and 20% of them were smokers. Find the probability that one randomly selected U.S. adult is not a smoker. Well, if your mind went straight to, okay, well, if 20% of them were found to be smokers and 80% are not, you are doing great. How that would look would be the capital P of not a smoker is equivalent to 1 minus the probability of a smoker, which is 1 minus that 20% or 0.2, which is 0.80. So if you right away got 80%, nice job. The probability, though, remember, is the corresponding decimal, 0.80. Relative frequency, skydiving example. In a recent year, there were about 3 million skydiving jumps, and 21 of them resulted in deaths. A, find the probability of dying when making a skydiving jump. B, find the probability of not dying when making a skydiving jump. So A and B are asking us about complementary events. Okay, let's set up part A, the probability of dying when skydiving. That would be equivalent to the number of deaths divided by the total number of jumps. So we had 21 out of our 3 million. If you type that in your calculator, you get 0.000007. That's the probability of dying when skydiving, according to this data. Move that decimal place twice, I'm just curious. That would be 0.0007% of the time. Okay, part B wants to know the probability of not dying. So that would be the complementary event. So, not dying would be the other 2,999,979 over the full 3 million jumps, equaling 0.999993. And hopefully you notice that those two values, probability of dying and probability of not dying, check those out right there. They would have to add, and they do add, to 1. New notation for us, capital P, so the probability of This is event B occurring, and then this vertical line right here, it kind of looks like an I or an L, but try to make it a little longer if you're writing on your notes. Make it a little longer to make it more obvious. When you get to this point, you say the word given. So this would be the probability that event B occurred given event A occurred. Here we have that written down for us. Example, data from a study of 2 airlines which fly to small town USA is given here in this table. So we've got on-time flights and late flights, Podunk Airlines and Upstate Airlines. And we have a frequency table here. A, if one of the 87 flights is randomly selected, find the probability that the flight arrived on time given it was an Upstate airline flight. All right, you guys, I want to talk about that word given. What we're going to do when we see given, whatever follows it, that's the only data we're interested in. We may be handed a spreadsheet with 100 tabs with all kinds of data about airline flights being late or on time. But as soon as we see this word given, it's kind of like saying, hey, ignore everything else. We just want to look at, and what it says after, Upstate airline flights. So I'm going to cover up this airline's flights because we're just not looking at that data. Like I said, you could be given a spreadsheet with 100 tabs. You're not always going to look at all of it. In this one, we're just being asked to look at, given it was an Upstate airline flight. Okay, so what they want from us is if one of the 87 flights is randomly selected, find the probability that the flight arrived on time. Okay, so just from this data here, on-time flights, there were 43. 43. So we set that up as notation, capital P, probability of, an on-time flight. Remember this right here we read as given. It was an Upstate airline flight. Cross everything out that is not an Upstate airline data. So there's our numerator, that's the 43, and that is out of a total of 48 flights here, because we have summation of these two, total of 43 plus 5, which is where that 48 came from. Okay. B, if one of the 87 flights is randomly selected, find the probability to 3 decimal places that the flight was Upstate Airlines given that it was late. Okay. Go to your word given, circle it, or deliberately look at it, and then everything that follows it is the only stuff you're interested in. That it was late, okay? Late. Ignore everything else except this given condition. It needs to be late flights only. That is all we're looking at. We're only interested in late flights. So I'm going to get rid of all this. This is about on-time flights. We're being asked to only look at information given that it was a late flight. All right, let's set this up. We're being asked the probability to 3 decimal places that the flight was an Upstate airline flight given that it was a late flight. So using just our numbers here, nothing else, we have crossed out everything else that is not a late flight. Our numerator for Upstate Airlines is here. There are 5 out of, how many total do we have that were late? 11. I think this one wanted us to round to 3 decimals. Oops. So let's type that in our calculator. 5 divided by 11. Accurate to 3 decimals, that would be a probability that 0.455. That is the probability of randomly selecting one flight and it being a late flight from Upstate Airlines. You can also, should they ask you for a percent, you can go with 46% Just depends on how they want the answer, and this one said to 3 decimal places, so we'd go here instead of the fraction. Finding the probability of at least 1. Let's start with this example to help us understand at least 1. A box of 65 watches contains 11 that are defective and 54 that are not defective. If you grab 3 watches from the box without replacing them, what is the probability that at least one of the 3 watches that you grabbed is not defective? Round to 4 decimals. Okay, we need to start by talking about this at least 1 situation. We've got 3 events that are dependent on each other. Why dependent? Because it said without replacement. So the probability of the first watch, whatever happens with that watch, changes the probability of the second. Whatever happens with that watch changes the probability of the third. So we're being asked, what is the probability of, so capital P open parentheses, at least one of the 3 watches we pick is not defective. Okay. At least one of the 3 watches is equivalent to, okay, so this next line, equal sign, this is equivalent to 1 minus the probability of all 3 watches you pick are defective. This is a little tricky to wrap your mind around at first. So what I want you to think of is 3 watches are pulled, how many being defective? Okay, well the full population would be, you could have 0 of them defective, you can have 1 of them defective, you can have 2 of them, or you can have 3 of them defective. So when we say at least 1, that would be 1 of them, or 2 of them, or 3 of them. That's what at least 1 means, 1 or 2 or 3, not 0. Hence why we're using the complementary event of 1 minus the probability that all of them, or AKA 0 of the watches, right here, 0, are defective. All right, we're going to set this up as keep your equal sign, keep your 1, drop your minus sign. Now this right here is going to turn into 3 fractions. We know that from the last couple sections. The number 3 here, so we need 3 fractions. First fraction would be 11 out of the 65. Where did that come from? Well, we're looking for the probability that the watch is defective, and we have 11 defective out of 65. So that's where the 11 out of 65 came from. Once that watch is taken out, the numbers change. Now we're down to 10 defective watches in the box out of a total of 64 watches. So second fraction, we take another watch out, 10 out of the 64, probability that we pull one of those defective ones again. That's where the 10 and the 64 came from. After we pull that watch out, these numbers count down. There are 9 defective left in the box and 63 total left in the box. That's where the 9 out of 63 comes from. All right, we type this in our calculator from left to right. Type it in carefully, and you should get 0.996. So it'd be, another way to think of it is 99.6% of the time we can pull 3 watches out of there, and at least one of them is not defective. All right, 3 adults are randomly selected without replacement from 247,436,830 adults in the US. Okay, that's not very many, okay? Just note that. 3 adults selected out of this many. All right, assume that 11% of adults in the US use drugs. Find the probability that all 3 selected adults use drugs. Okay, what we're going to do is address what I was pointing out. The 3 is a small sample considering the population size. We're going to address that using what's called the 5% guideline for cumbersome calculations. Here it is. When sampling without replacement, which is what we have, and the sample size is smaller than 5% of the population. Like this 3 right here. This 3 is way less than 5% of the population. What is 5% of this? Let me just type it in my calculator real quick. I'm going to type in that full population, 247,436,830 times, I want to know what 5% of that is, so 0.05, enter. So it's 5% of that full population looks like 12,371,841. So we sampled way less than 5%. Okay, so that being noted, what the cumbersome calculations 5% guideline is, it says that we can treat the selection as independent. So we don't have to adjust the numbers, like take one of those adults out and then take the population down to 247,436,829. Then take another one out and then adjust the population down by 1 to 247,436,828. This is saying you sample less than 5%, decreasing this large number by 1 each time isn't going to affect your numbers at all. So we can just write it as probability that all 3 adults use drugs. That would be the probability that the first one we pick uses drugs, and the second one, and the third one. I'm overkill with the ands, because remember the word all makes it an and statement, and making it an and statement makes it multiplication rule here. So this all led from the word all 3. Okay, at this point we get to write our fractions out, and like I said, we don't have to count down. We just get to go straight for 3 out of this many. Oh, sorry, no, we get to go straight for 11% of the adults in the US use drugs. That's where this came from, the 11%. 11%. And the second person drawn, we've got an 11% or 0.11 probability that they use drugs. And then the third person is selected, and there's a 0.11 probability that they use drugs. In math, instead of writing it 3 times and multiplying, we could just write to the third power, getting us 0.11 to the third, which is equal to 0.001331, which means that there is a 0.001331 probability that all 3 selected adults use drugs. It's like less than 1% there for that answer. All right, that brings us to section 4.4. In section 4.4, we're going to talk about 3 different counting rules. So title, 3 counting rules. First one, it's called the fundamental counting rule. It's the number of ways a set of events can occur when the first event can occur m many ways, then the second event can occur n many ways, the third event can occur o many ways, the fourth event can occur p many ways, and so on. See this here? So it would just be m times n times o times p. Let's look at an example. Applebee's offered a special 3-course dinner for $15.99. The menu included choices of 3 appetizers, 4 entrees, and 2 desserts. How many different 3-course meals can you order? So we're being asked for a count. How many? How many different 3-course meals can you order? Well, looks like you've got 3 selections to make. You have to choose an appetizer, then you get to choose an entree, then you get to choose a dessert. So we're going to multiply the number of ways the appetizers could occur times the number of ways your entree choice could occur times the number of ways your dessert choice could occur. So it's real simple. It's just 3 times 4 times 2, because you could choose 3 different appetizers, 4 different entrees, and then 2 different desserts. Multiply those together, and it turns out there are 24 different 3-course meals that you could order for this Applebee's special. Let's try another one. How many different 5-digit passwords exist using only lowercase letters if repetition is not allowed? Okay, we need to make a 5-digit password. We're only allowed to use lowercase letters, and we can't use the same letter twice. Hint, there are 26 letters in the alphabet. What is the probability of someone guessing your password in one try? Okay, for them to guess it in one try, that'd be 1 out of, how many possible passwords are there? Well, when you're creating a 5-digit password, you have 5 decisions to make. The first decision you make, you have 26 letters to choose from. You can't repeat one of those. So the second decision you have to make when you're making your password, you've got 25 letters to choose from. Okay, imagine that. You're making your password. You're going to select the third number for your password. Third letter. Lowercase letter, no repetition. So you've got 24 to choose from. The fourth letter in your password, you've got 23 to choose from. And the fifth letter in your password, you've got 22 to choose from. So the fundamental counting rule, just multiply them all together, and it turns out that there are 7,893,600 passwords that exist that are 5 digits using only lowercase letters and not repeating any of the letters. All right, so what's the probability of someone guessing yours in one try? It'd be 1 out of that total number. The second counting rule we're going to talk about is the permutation rule. It's the number of different permutations when n many different items are available and r many of them are selected without replacement. Okay, so for this particular type of question, we're going to have to use technology, and unfortunately, StatCrunch does not have this program. So what I would suggest is that you download a free graphing calculator app. It does not have to be the best one. Just get a free graphing calculator app. My favorite one, which I think is the best for statistics, is Graphing Calc 83. However, now that I use a spreadsheet, I don't refer to that graphing calculator app anymore, but it's really good. If you ever find yourself in a stats class that's not using a spreadsheet, I would suggest Graphing Calc 83. It's not free though. It used to be free, but as people figure out, it's really the best one, especially for statistics. They've been able to charge, which is good for them, making a good product. Free Graphing Calc app. Okay. So we're going to need to use that app. It's going to have a menu called Math. And then we're going to look for this right here, PRB. It stands for probability. All right. Let's look at an example, and then we'll try to pull that up on a free graphing calculator app. Oh, we're not quite ready for an example yet. When we're talking the permutation rules, we want to think that the different positions matter. For example, President Biden versus Vice President Harris. Okay, they have those positions. That is a very different outcome than if we have President Harris and Vice President Biden. Remember, this section is about counting. So if we're talking the different permutations, those positions changed. Therefore, we would count each of those as a different permutation. So this right here would be one permutation, and this right here, we count it as another one because these positions made it different. So this is 2 permutations. This is how we count permutations. If rearranging items changes the outcome, then we use permutations to count all of the possible outcomes. All right, now let's try an example. There are 9 members on a board of directors. If they must elect a chairperson, a secretary, a treasurer, how many outcomes are possible. Okay, notice they're talking about giving them positions, 3 positions actually, out of 9 members. Okay, so we're going to be selecting 3. That's 1, 2, we need 3 people. The 3 is equal to our R. The total number that we have is 9 members. So we're going to choose 3 of the 9. 9 gets the lowercase n. Okay, so when we open our free graphing calculator app, whatever one you guys chose, go ahead and open it now. You want to find the key that says math, okay? Just going in order from right here. After it says technology, then it says math. Hit the key that says math. Somewhere on that screen, mine is at the very top, and I have to arrow over 3 times. We're right here. We're looking for PRB for probability. So for me, I'm going to arrow over. Actually, mine's touch screen, so I'm just going to touch where it says PRB. The next thing on our screen that we're looking for is NPR. So I'm going to select mine, opening that program. Next thing we need to do is this task here. Enter N and R. N is 9, R is 3. Make sure you enter them in the correct place. It goes N, followed by the capital P, followed by R. So it would look like, let's see if I have it here. Doesn't look so great. It would look like N, so 9, capital P, and then R, so 3. This is what it should look like on my calculator screen, okay? On our calculator screens. 9 and 3. When I run that program, it's going to give us a count. So mine came out as 504. So, given 9 board of directors, if you select 3 of them for different positions, that is 504 permutations. Let me erase some of my stuff here. It's kind of cluttered. All right, another example. A history pop quiz asks students to rearrange the following presidents in chronological order. So years, numerically in order, numbers. Hayes, Taft, Polk, Taylor, Grant, and Pierce. What is the probability of guessing correctly? All right, so this student has to put 1, 2, 3, 4, 5, 6 presidents. So they would have to choose 6 out of all 6. They have to use them all in their guess. Or I'm sorry, on their test. It might be guessing, I don't know. So to choose 6 out of all 6, you got to choose them all. And we're going to see how many permutations there are. We run that same program in PR, where N is 6 and R is 6. And it turns out that there are 720 different permutations for those 6 presidents, which means the probability of that student guessing, just random guess, they've got a 1 out of 720 chance of guessing correctly. All right, that's our second way of counting, called the permutation rule. The third way is called the combinations rule. And that's the number of different combinations when n many different items are available and r many of them are selected without replacement. Very, very similar to the last one, okay? The permutation rule and the combination rule are very similar. So even with our technology, you're going to use a free graphing calculator app. You're going to select math. You're going to find the PRB on your calculator, and then look at the difference here though. If we're counting permutations, we used NPR. But for this one, combination rule, we're going to be counting how many combinations. So you're going to want to locate the program NCR. You'll enter N, which is the number you have to select out of. R is the number total available, and then you'll run it. Now with combinations, you don't think positions, okay? Permutations, you count if positions change the outcome. Combinations are different. For combinations, you just want to think about committees. A committee with members Obama and Bush is the same as a committee with members Bush and Obama because they don't have set positions. They're just committee members. So this would count as one combination, and this would count as the same one. This is the same combination, so it wouldn't go 1, 2. Permutations get counted. There are more of them typically because every time the positions change, you count it as another. It didn't matter that these were swapped here because we're just talking about a committee, no set positions. So we're talking combinations. If rearranging items does not change the outcome, then we use combinations to count all the possible outcomes. Example, there are 9 members on a board of directors. If they need a committee of 3 people for a project, how many different outcomes are possible? So here we want to recognize, okay, this isn't permutations. They're not selecting president, secretary, treasurer, whatever it was on the last slide. They just need a committee of 3 people. So hit the math key, probability, and open this program this time, NCR. Enter your N as 9 again, 9 board members, and R is, well, they need a committee of 3 people. Run it, and you'll find that if you have 9 members, you choose 3 for a committee, there are 84 possible outcomes. I wonder how many permutations there were when we went positions. 504. That's quite a smaller amount of combinations. Another example, in a match 6 lotto, winning the jackpot requires you select 6 different numbers from 1 to 49. The winning number may be drawn in any order, okay? Winning numbers, any order. What's the probability of winning with 1 ticket? All right, please notice that it says in any order. That's the key. It doesn't matter which order, just like a committee. They're all on there, okay? You don't have to pick a certain one for president. That is, in this example, you don't have to pick a certain number first. Just no order. So that should identify for us here that we're being asked to count the number of combinations, not the number of permutations, because we can draw them in any order. Okay, run your NCR with N equals 49, because remember it's 1 through 49 to choose from, and R equals 6, because you have to pick 6 numbers to play. Run it, and you'll find that there are 13,983,816 outcomes for that lotto ticket that you could buy. So your probability of guessing correct first try, 1 out of almost 14 million. That will finish our discussion for Chapter 4. My name is Emigh. Thank you for being here.